In a previous video on differentiation, we saw that the rule to differentiate something like, x cubed or x to the 4 or x to the n in general is to take that value and put it in front and then to reduce the power by 1. So x to the 4 becomes 4x cubed, x to the n becomes n x to the n minus 1 in general. And I said that that rule extends to other values, not just whole numbers. So, for example, if I wanted to try and differentiate something like y equals 1 over x, we could still do that using this rule. We'd have to, be convinced that it works, and it does work. But this is actually just an example of something of this form in a way, because I can rewrite 1 over x as x to the minus 1. And if we apply this same rule, nx to the n minus 1, what I'd get is dy by dx. Well, this time, rather than n being a positive whole number, we've got n is minus 1, and so that would mean that n minus 1 would be minus 2. So the derivative here would be minus 1, or just, so I can just put minus 1 times x to the minus 2. Putting that back in the original form, you could, if you wanted to, write that as minus 1 over x squared. So to do these, you need to be good with indices, so look back at the videos on indices if you're not sure what I'm doing with the switching this to this and this to this. But basically that rule applies in just the same way. If I had y equals 1 over x cubed, that's the same as saying that's y equals x to the minus 3. So here we'd have n equals minus 3 and n minus 1 would be minus 4 then. So I'd get dy by dx equals minus 3 times x to the minus 4. And the other rules that we mentioned before about multiplying by constants and adding things together still work. So if I had y equals 3 divided by x to the 7, that's the same as y equals 3 times x to the minus 7. So again, here we've got n equals minus 7, so n minus 1 would be minus 8. And that means that dy by dx would be, well, we'd multiply it in front by minus 7, so we're going to get minus 21 x to the minus 8. So if I wanted the gradient of this function, at x equals 1, say, I'd just say that dy by dx equals minus 21 times 1 to the minus 8. 120 power is just 1, so actually this would just be minus 21, and we could do that for any other point as well. We might need to use the calculator to work out some of the powers of minus 8 there. One more then, so if I had, let's say I had y equals 4x cubed plus 2 over x, well, dy by dx, I can differentiate these term by term. So 4x cubed, as before, differentiates to 12x squared, and 2x over 2, well that's, 2 over x, that's 2x to the minus 1. So I can just differentiate that with n equals minus 1. Minus 1 multiplies out in front, so I get minus 2, and minus 1 reduces by 1 to minus 2. So that's really neat. We're able to work out the gradients of quite complex functions, functions that we might not obviously know how to draw even, by we don't have to draw their graphs, by just applying this rule. And it turns out we can go even further than that, not just whole numbers, but something like y equals the square root of x. Well, you could write that as y equals x to the 1/2. And now we'd have n equals 1/2, and n minus 1 would be half minus 1, which is minus 1/2. So dy by dx would be 1/2 x to the minus 1/2. If you wanted to do the cube root of x, that would be y equals x to the 1/3. So we've got n equals 1/3, and 1/3 minus 1 is minus 2/3. So that gives us dy by dx is equal to 1/3 x to the minus 2/3. And again, we could multiply these by constants and add them together, whatever. So I could do y equals 7 x to the 6 plus 3 times the square root of x, and I would get dy by dx is equal to 42 x to the 5 plus 3 times the dy by dx for root x, So 3 over 2, just multiplying this by 3, x to the minus 1/2. So the fact that this rule works for all sorts of powers, not just whole numbers, you've got fractions, negative numbers, this is a really powerful result that allows us to suddenly differentiate all sorts of functions.